So let us start. So today we will cover chapter 4, which will involve round-off and truncation errors. So we will learn what is round-off and truncation errors and how we can minimize them. So to start with, the chapter objectives will be to understand what is the difference between round-off and truncation errors, and understand that these errors can come from numerical solutions, and this is why we can call them numerical errors. And we should know how to control them and what will be the cost of minimizing these errors. To start with, we will talk about round-off error. So whenever I have a number, when I use a machine, sometimes I should be restricted to a certain number of digits. So for example, if I tell you I want to present radical 2 on a computer, okay, I should know the capacity of my computer. So my computer can store 5 numbers, 10 numbers, 32 numbers. So it depends on its capacity, okay? Now we know, for example, that radical 2 is equal, it's an irrational number, so it has infinite number after is a comma. And we have, for example, it is 1.4142135 etc. It's we have infinite numbers after the comma. This is why here what we will do, depending on the precision of our machine, we will decide what will be the round-off error that will be induced. Okay? So for example, I can tell you that your computer can only store 5 digits. In this case, radical 2 for the computer will be just seen as 1.4142, and it will stop here. It cannot read the remaining part. In this case, for just radical 2, the round-off error will be the difference between radical 2 minus 1.4142. Okay, so I can say that my computer, when reading radical 2, will induce a certain error equal to the difference between the exact value of radical 2, which we can never have the exact value because we have infinite number of digits after the comma, but at least if we take a very large number, we can be more close to the actual value of radical 2. So if the computer can just store 5 numbers, this will be the error induced, and this is called the round-off error. And as you can see, the round-off error will be dependent on the machine I use. If it's a high precision machine or high-end machine, this means that it can store a high number of digits, and then the error will be small, because higher the number of digits I can read, lower will be my error. So for example here, if I say I will move to a calculator, let's say, that can store 10 digits, then the number I will read is, I will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can read until this point. So then my error will be, instead of being of the order of 10 minus 5, my error will be of the order of 10 minus 10. So by increasing the number of digits that can be stored by the calculator, the computer, or the machine, I can reduce the round-off error. Okay? Now, just let me check your questions. Okay. So, let us consider now what will be the error, let's say, in computing radical 2 minus 1 using, let's say, the calculator. Okay, so I want to compute the error when I do radical 2 minus 1. If I can, if my calculator can store, let's say, 5 digits, then it will replace radical 2 by 1.4142. For 1, there is no error induced because it's 1 is represented by 1. So when I do the round-off error, I will obtain that it is equal to the difference between radical 2 and the value that can be stored in the calculator, which is 1.4142, and it will be of the order of 13.356 times 10 to the power minus 5. So because here, when I do the difference, this term will cancel out, and I will end up with 0. Okay, 135, etc. times 10 to the power minus 4. So if I take 1 to the other side, it will be 1.356 times 10 to the power minus 5. And if I want to take, if I want to be more accurate, I will take everything, all numbers that I have here. So the error will be 1.3562373095048 times 10 minus 5. So my error is of the order of 10 minus 5 in this case. Now, by just saying that my calculator will store more digits, my round of error, of course, will be reduced, because when I take 10 digits, okay, what will happen then is that I will reduce the error by taking a larger number of points. Okay, so I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I will have this number will be taken into consideration. So when I do the difference, between the two, I will just get now that the round of error will be 3.73095, etc. Okay. So in this way, the order, by increasing the number of digits from 5 to 10, the round of error was reduced from 10 minus 5 order to 10 minus 10. Now, concerning if I want to do addition on a calculator. Okay. Now here we have given an example. Taking into consideration, guys, can you mute your microphones if you are not asking questions, please? Because there is a lot of noise in the background. Please mute your microphones. So here, if I want to do the addition of 1.1, guys, please mute your microphones. Can you please mute your microphone? So if I want to add 1.1 to 2 on a calculator, okay, we will see when we do the analysis how calculators and computers operate. We will see that in general, they work in binary systems, not in decimal systems. What do we mean by this? So any number I have can be represented in decimal or binary system, okay? In case I consider that I want to present a number in decimal system, this means that, for example, if I take 129, I can represent 129 in the following way. I can say it's 100 plus 20 plus 9. And when I talk about, when I talk in a decimal base, this means that it can be represented as coefficients times 10 to the power of a number. So it's 9 times 10 to the power 0 plus 2 times 10 to the power 1 plus 1 times 10 to the power 2. And when I say I represent a number in decimal system, in decimal base, okay, this means that I am working in a base of 10. So when I want to read this number, I will take 10, I have that 10 to the power 0, the coefficient of 10 to the power 0 will be the first number from the right side. The coefficient of 10 to the power 1 will be the second number, so it's 9, 2. And the coefficient of 10 to the power 2 will be the third number. And in a decimal system, I can have numbers going from 1 to 9. Okay? Now, I can use another representation for numbers. I can change the base. I can work in any base I want. Okay? So you have binary systems will work in base of 2. So for example, if I have, let's say, let's consider any example. So for example, if I take 6, okay? Number 6 in base 10. I want to write it. So just 6 in base 10 is just 6 times 10 to the power 0. Okay? So it is just 6. Okay? Now, if I want to represent 6 in a certain system of base 2 instead of base 10, sorry, it's 6 times 10 to the power, yes, because 10 to the power 0 is 1, okay? So in base 10, it's just the coefficient of 10 to the power 0 is 6. So it's the first number here from the right side. And we don't have, it's plus 0 times 10 to the power 1, etc. So we don't have to put anything because you know that any 0 to the left will not be taken into account, okay? So now I want to transform this number. Instead of expressing it in a base of 10, I want to express this number in base 2. If I want to express it in base 2, I will have to do the following. I can write it as 4 plus 2, okay? So I can say that it's equal to, if I take, it's 1 times, so it's 2 times. So if you write 4 and 2, how you can convert 4 and 2, and you can say also it's plus 0, okay? How you can convert these numbers 4, 2, and 0 to a base of 2? You can say that 4 is 1 times 2 power 2. And you can say that 2 is 1 times 2. And you can say that 0 is 0 times, so this is 2 to the power 1, plus 0 times 2 power 0. So now, if you want to read your final number in base 2, you will start as we did for 129 in base 10. You will do now, what is the coefficient of 2 to the power 0? It's 0. So I start from 0 here. Then, what is the coefficient of 2 power 1? It's 1. So I put 1. And what is the coefficient of 2 to the power 2? It's also 1. So my number will be, this is 6. In base 2, 6 is 110. So always, in general, we don't specify because by default, the base is 10. So if we don't put anything, this means that we are working in base 10, okay? But we will see that for the world of computers and calculators, they mainly work in binary systems. So numbers in calculators and computers are just represented by 1 and 0s. Okay, so you don't have until 9. Any number you give to the calculator, it will convert it to a binary number to perform any operation. Okay? Now we will see after in this chapter a method that will allow us to go from decimal to binary in a simple way. Okay? Here for x6, for example, it's easy because you can directly decompose it in 4 plus 2. But sometimes if it's a complex number, so the method, you should have a method, standard method to develop to go from one base to the other. Okay? So this is why sometimes I cannot obtain 100% the expected result. If I say 1.1 plus 2, it's 3.1. But on the calculator, it will be little bit different than 3.1. I'll tell you why. Because 1.1 is 1 plus 0.1. In decimal system, 0.1 is a rational number. It has a finite number of digits after the comma, so it's fine. But if you convert it to binary, you will see that in binary system, 0.1 is a non-ending number. So you have 0.0999, etc. We will see how. Okay. So in this way, when the calculator will add in binary system, okay, what will happen is that I will get a certain error due to this fact that when I convert to binary system and then I go back to the decimal system, 0.1 will be 0.0999 and not exactly 0.1, because in the binary system it's not an ending number, okay, it's an irrational number. So I will have to have a certain, I will have a certain error, but of course the error will be very small. It will be maybe of the order, let's say 10 minus 8. So it's fine for me if the error is of the order 10 minus 8. Now, concerning the precision, we can have equipment of different precision. Okay, we can have double precision. For example, if the round of error is 10 minus 16, this is called a double precision equipment. For smaller, for higher round of errors and therefore smaller precision, a single precision device is where the round of error will be of the order of 10 minus 7. Okay. Now you can try to see the precision. You can try, for example, on your phone. The calculator of your phone in general is single precision. It's not as accurate as Excel or as your computers, because it cannot store, it can store a certain limited amount of numbers, more limited amount of numbers. So the precision of the equipment will depend on the number of digits it can store. This is an example involving what you were talking about. Okay, so let us say we have a digital clock that increments each 0.1 seconds. Okay, so we have increments each 0.1 seconds for this clock, and this clock, okay, is based on a single precision digital clock. Of course, higher is the precision of the clock, better will be its accuracy. Yes, Karen, this is the method you are talking about to go from decimal to a binary. It's true, but we will develop it after in this chapter. And also, you have, if in case your number is smaller than 1, then you should do the opposite way, and you should multiply by 2 until getting 1. Okay? We will develop these methods later in this chapter. So here we give an example where we have a single precision digital clock increments that have increments each 0.1 seconds. Now, because it's single precision, each 0.1 second we will have a certain error. You know why? Because as we said, in general, computers, calculators, digital equipment work in binary systems. So for this calculator, 0.1 second will be, which is a decimal number, will be transformed into a binary number. And we will see when we will develop the technique, we will see that 0.1 in base 10, okay, is an infinite, it's a number with infinite digits after the comma. So it will not, when I go back to the base 10, okay, I will not exactly have 0.1. I will have nearly 0.0, here just we have a 0, 0.099990463, etc. So this will induce an error. So by going from decimal to binary base and then going back to decimal base, because you know that for your calculator at the end will display a number in the system, decimal system. So on your calculator, when you can put numbers until 9. So you can put just, let's say 9 plus 5, it will give you 14. But how will operate the calculator? The calculator will not add 9 plus 5 as they are. it will convert 9 to base 2, and it will convert 5 to base 2. Then it will perform their addition in base 2, and after getting the result in base 2, it will transform it back to a decimal, to a number in decimal system. So this will here, for example, in certain cases, it will not induce an error. It depends on the conversion from base to base. Okay, so here, for example, no error because it's a finite number in both bases, in base 10 and in base 2. However, 0.1, which is a rational number in decimal base, when I go to binary base and then I transform it back to decimal base, I will get an irrational number. So this will involve a certain error. This procedure of going from one base to other to perform the operation will induce a certain error. So if we consider the single precision clock, 0.1 after this transformation will give us 0.9999046, okay, which is a little bit different from 0.1. Here you can say, but it's negligible, this error. Yes, it's right, completely right. If you do the variation, the difference to find the round off error, all you have to do is to do 0.1 minus 0.0999. You have 1, 2, 3, 4, 5, 6, so it's 6, 9. And then 0.463. It will nearly give you 9.537 times 10 minus 8. And in case you want to, so each increment, you will have this round of error, okay? So in total, after 1 year, your round of error will be much higher because it will accumulate. Okay, so if you want to compute the total round of error, you will say that in 1 second, I have 10 increments because each 0.1 seconds I have an increment. So in 1 second, I have 10 increments. Therefore, if I want to compute the number of increments in, let's say, 1 day, I should multiply. So if I want at the end, after 1 year, first I convert to days, then I should multiply by 365. Okay, so in 1 day, I should multiply by the number of seconds. So if each
Doctor, why is it
second I have 10 increments. Sorry?
Why is it 1 second, not 0.1 second?
No, هي الانكريمنت هي 0.1 second, صح؟ بس انت you want to see after 1 year how much will be the total error. Okay? انت each 0.1 second you have 1 increment, مظبوط؟ So you want to compute, in order to compute the total error, you should know how many increments I have in 1 year. If in 0.1 second I have 1 increment, in 1 year, how to compute the number of increments in 1 year? You will
know
say,
how many
yes,
1 second
you
in
say
1
that 1 year include how many seconds? In 1 year I have 365, which is the number of days, times 24, which is the number of hour in a day, times 3600, which is the number of seconds in 1 hour. And then, since each second I have 10 increments, I then should multiply by 10. So it will be times 36,000. Okay. And then I multiply by the round of error in 1 increment, which is 9.537 times 10 to the power minus 8. In this way, هلا هون كان في typing error. I will fix it for you بالslide. Okay, in the slide posted on Blackboard, I will fix it for you. So you have after 1 year nearly 30 seconds of lag. Okay, so it depends on your application. You decide if you say it's acceptable or not. If you are working, for example, you have a space mechanics application, you have a rocket and you need to follow the path of the rocket, 30 seconds might be a very high error. It might be unacceptable. If you just want to see what is the time, so you have a clock, a normal clock, and you want to assess the time, having an error of 30 seconds in 1 year is fine. Okay, so depending on the application, I can decide if an error is acceptable or not. The typing error, yes, أنا هظبط لكم التايبنج error. Typing error here 0.1 second مش 0.01. أنا ظبطتهم already بس الفايل I opened it بالغلط رجعت بعتت الفايل القديم. It's not a problem. I will post on Blackboard the actual file. Okay. So here you have 0.0.1 is 0.0999. And then here after 1 year, I should multiply by the number of increments. So I multiply by 365 times 24 times 3600 whole number of seconds. بس بما انه الانكريمنت is each 0.1 second, and I should multiply by 10. So instead of having 3600, I will have 36,000. Okay, times the round of error per increment. يعني per increment I have an error of 9.537 times 10 to the power minus 8. So I get in total 30 seconds as error. Okay. Any question on this? Okay. Now we will move to the second type of errors, which is truncation errors. Okay. In truncation errors, the error is method dependent and not depending on the machine precision. So this is the first difference between round of error and truncation error. Round of error is depending on the precision of the machine. Truncation error is depending on the method that I am using and how many terms I want to keep and how many terms I want to eliminate. We will take an example of a truncation method, which is a very common example, the Taylor series expansion. Okay. I think you have already seen what is Taylor series. Taylor series is a method to approximate a function around a certain point. Okay. And this series include, it's a polynomial that has infinite terms. Okay. And you know that if I want to perform calculation, I cannot add infinite terms. I will select a certain number of terms to add. So depending on the number of terms I select, I keep, the truncation error will vary. Of course, higher is the number of terms I keep, higher will be the accuracy, and lower will be the truncation error. Okay? So for example here, the general expression of Taylor series expansion of a certain function of x about x equal a is given by f of x is equal to f of a plus x minus a times the first derivative of the function at a plus x minus a squared over 2 factorial times the second derivative of a. And the general term for any term is the following. It's x minus a to the power n over n factorial times the derivative of order n at a. And n factorial can be computed as 1 times 2 times 3 until times n. Okay. Now, as you can see here, the right-hand side of your equation represents an infinite series. And if you want to have an exact value of fx, you should compute infinite terms and add them, which is not feasible. Okay? This is why using Taylor series, you will have an error because you will stop at a certain stage. Okay? Now, this is called truncation error. Now, in case you increase the number of terms that you will take into account, so more you add the terms that will be calculated, lower will be the truncation error because